Hi guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the RX 5700 XT Reference PCB from AMD. So, the funny thing is, this is actually kind of like one of the better 5700 XT PCBs you can get. Most of the cards that come with custom air coolers actually downgrade from this design because this design is really not what you would call cost optimized. As AMD has seemingly made a lot of decisions, like there's some decisions which are basically to accommodate the blower heatsink, and some decisions just like they're expensive and I can't figure out why they were made.
Before that, this video is brought to you by Corsair's Hydro X water cooling series. Corsair's strength is bringing water cooling to the masses, and it has built out cooling solutions with industry leaders to help newcomers get into open loop cooling. Corsair has fittings, adapters, GPU water blocks, CPU water blocks, pump res combos, and radiators, all available in the Hydro X line. As you can see in our footage, these kits can be used to build beautiful open loop systems. Learn more at the link in the description below.
So yeah, let's get right into it, because it also means that this is like, honestly, if you're water cooling, like I would just go straight for this PCB. Like if you're going to water cool a 5700 or, well, the funny thing is, because it's so not cost optimized, the 5700 actually loses a phase for its reference PCB, because it's like, yeah, we need to save money somewhere, and shaving off phases is one of the easiest ways to do that. So anyway, but for the 5700 XT, like this is actually like, if you're water cooling, just go for this PCB. I don't really see a point in worrying about like getting a custom card with a custom PCB, because unless you're buying like a Strix or a Red Devil, you're not going to be getting a better PCB than what the reference card offers anyway. And even then, it's like yeah, basically you're not going to get anything better than the reference card. So let's get into it, shall we? So the VCore VRM is this right here. And that is a 1, 2, 3, 4, 5, 6, 7 phase. And those are all very real phases. So if we go on to this side of the card, we have this voltage controller right here. That is a IR 35217. This goes up to 8 phases total. Here it's running as a 7+1. So the 7 phases handle our VCore. The +1 handles our SoC, or at least what I assume is the SoC. I've never actually gotten a confirmation on which rail is what, and there's sort of a lot of little regulators, and I'm just like, there's basically 2 regulators, like one of them is for the SoC, one of them is for the VDDCI rail, and I'm just not sure which one is which, but the parts on both of them are exactly the same, so it's kind of like it also doesn't matter. It's mostly a location distinction. Actually, on this card especially, it doesn't matter, because AMD opted to use the same controllers, whereas on some of the like the custom cards, they'll often actually use a cheaper controller for the second one. But anyway, so the 7 phases are for our VCore. So yeah, we've got a really nice high phase count. Like 7 phases is pretty up there for reference PCBs. And for the actual power stages, we're looking at a bunch of, damn it, I forgot who makes them. Ah, there we go in my notes. Fairchild Semiconductor, which is now owned by On Semiconductor, so you can consider them the same thing. These are Fairchild Semiconductor FDMF3170s. So these are 70 amp smart power stages. And what makes these special is that they're smart and they're 70 amps. So the 70 amp part just means they're ridiculous, like they can handle a stupid amount of current. The smart part of that smart power stage label means that basically they internally monitor temperature, they monitor current. Actually, they have a more accurate monitoring system for a more accurate current monitoring system built into them than what you'd normally find on, like, there are some past generations of power stages which would monitor current internally as well, but they wouldn't necessarily be like this is basically a new specification for higher accuracy current monitoring, which Intel basically created for their server stuff. And well, now everybody's making piles and piles and piles of these because Intel server hardware is extremely popular, so you just have tons and tons of power stages designed around Intel's spec for that, and well, they find their way into things like GPUs. These are also the same power stages that like NVIDIA really likes to use for the same reason. They're just insanely efficient. They have built-in current monitoring, built-in temperature monitoring, overcurrent protection, over temperature protection, and a bunch of other protections that I don't even like. There's so many protection features built into these that I don't even remember all of them off the top of my head. So basically, that's what makes a smart power stage smart. It does also mean that it somewhat simplifies the design of the voltage regulator, as you like with a lot of other like really basic power stages. You actually have to build your own external current monitoring circuitry and you actually have to add a temperature sensor because there's not one built into the power stages themselves. So, well, they'll have a temperature like over temperature warning system, but they won't have a readable temperature sensor. So if you actually want to know what VRM temperature you're at, you can't get that data because it's not being measured. So you need to add an external sensor for that. So yeah, these somewhat simplify design, but they are still far, far more expensive than, well, just using cheaper power stages and building everything else around them. So the reference card is actually the only card that uses these. Everything else is on other types of power stages. The card that comes closest to these is actually the Strix from Asus, which, if I remember correctly, uses 60 amp smart power stages from Infineon, which are even more expensive and not really any less efficient, even though they do have like a 60 amp decrease in current rating. Like the efficiency curve, like it's kind of interesting. Like the 60 amp smart power stage from Infineon has basically the same efficiency curve as the 70 amp from Infineon. So I'm not sure how they got the different ratings on them, but if you compare the data sheets, it's like these look almost identical, except for the one fact where one of them is like 60 and the other is 70. So anyway, but these are basically really, really nice power stages. Though as far as smart power stages go, these are some of the cheapest you can get, which doesn't really mean much because they're smart power stages and therefore more expensive than basically all the other power stages you can get. Well, now there's POW IR stages like IR3555s or you have the power stages with exposed switch nodes. Those are insanely expensive just because of the packaging being extremely complicated to deal with. So yeah, but these are definitely these are definitely what I'd consider a high-end part compared to what we see on a lot of the sort of custom cards where you basically see power stages that they're not bad, but they're like the cheapest 55 or 60 amp power stages you can currently get from Vishay or On Semiconductor. And they're not bad parts. They can handle a lot of current. It's just like they're very like their claim to fame is that they're extremely cheap. Like it's the main reason those parts were created, is like we have technology to make high current power stages cheaper now. Way cheaper than they used to be, and so that's how we got those. Anyway, for the following operating parameters of 1.2 volts output, 500 kilohertz switching frequency, which the VRM may very well not be running at. It could be running below that quite easily, and 5 volts drive voltage, which I ran out of space for that, so I'll just put that down here. So 5 volts drive, which the 5 volts drive voltage is probably generated by this regulator right here. It's kind of small and kind of out of the way to do really anything else, so I'm assuming that's the 5 volts drive. So it's our 5 volts. So with these operating parameters, which this is the only voltage, well, you can overvolt the power stages, it's just going to decrease their lifespan. So this is really the only voltage you want to run them on, and they're optimized for this voltage as well. So anyway, so for these operating parameters, the VRM will sort of kick out the following amounts of heat. At 150 amps, it will produce about 14 watts of heat, which is a very slight advantage over basically all of the other cards out there, except the Strix, if I remember correctly. 200 amps, you're going to be looking at about 19 watts of heat, which again is a very slight advantage over everything else except like the Red Devil and the Strix. 250 amps, you're going to be looking at about 27 watts of heat, which is also still a slight advantage in favor of this card over basically everything else except the Strix. You get the idea. Basically, if you want the bestest VRM for a 5700 XT, there's the Strix. I don't really see a point in getting that though, because even like even this right here is great. Like, this is a great efficiency figure to have. And if you're throwing a water block on this, then it's like I don't think you're going to notice a difference going from like this PCB to the Strix PCB. I don't really think it'll help you in any way. So yeah, that's kind of like the Strix kind of, takes the 5700 XT PCB to the arguably illogical level of overkill. This I think is already really, really nice. And this is just the reference card. So 250 amps, 27 watts of heat, and 300 amps, you're going to be looking at about 35 watts of heat. 350 amps, this will be producing about 47. And the absolute maximum, the data sheet stops at 60 amps for 70 amp smart power stages typically. And that's done because nobody actually, the thing is, they are technically capable of handling a 70 amp current. The main issue with doing that is that the power stage will produce so much heat that, you'd basically have to design your VRM to have one power stage for 1 square inch of PCB. So it'd be like, here's a phase, and then here's your next phase. And then somewhere down here, you'd have your next phase, right? So, and then you'd have to have a heatsink on top of that and some airflow. So it's not really a practical current rating. It's more it is a real world, it's a rating that you can test the part to, but it's not a rating you want to actually use in a real world design because it's going to run insanely hot unless you're running water cooling over the VRM or something. So yeah, that's why ultimately the datasheet stops at 60 amps, because it's nobody's actually going to want to run them above that anyway. Actually, even at 60 amps, they are going to produce an insane amount of heat. Which in this case is going to be, for 420 amps for the output, you're going to be looking at about 67 watts of heat, which is a lot. It's not impossible to cool, but it is a lot of heat. And the best part is, with a 5700 XT, I'd be very surprised if you ever got past the 300. If you ever get past the 250 amp current draw on ambient cooling, I'd be very, very surprised. You might see peaks exceeding that, but average current draw is very, very I'd be very surprised if you could get the average current draw past 250A, because that would mean that the core alone on this GPU would be pulling close to 300 watts, and that's ignoring everything else on the card, right? So yeah, though it's not impossible. You'd probably just have to overvolt the card to 1.4 volts ish. And it's, I do wonder if it would actually scale to that voltage. So it would be an extra, it could be completely pointless to push that much power into the core. Anyway, so yeah, the VRM efficiency here is absolutely great, because you've got a 7-phase with basically, there are 70 amps more power stages that are slightly more efficient, say the Infineon 70 amp power stages, or even their 60s, because those are so similar to the 70s that they make. But this is pretty much as good as it gets. There are a couple cards that get a better VRM than this, but really this right here is absolutely great. So yeah, we've got a really, really nice V-Core VRM for the reference card. For the memory power, and this is where sort of the reference card gets silly, is just AMD evidently just refuses to use anything but the FDMF 3170. Which is basically, I think, one of the reasons why we don't actually see this PCB used on anything but the reference card, because memory phase 1, memory phase 2, so that's our VMEM, so that's our memory VRM, and this funky layout, I think, is done to optimize power distribution to the GDDR6 chips. Basically, because what tends to happen throughout the power plane is, if you have your VRM over here, by about here, you're going to have less voltage than you had over there. And you can see a lot of cards try to basically what you'll see in GPUs is that you'll have your bulk capacitance right off the VRM right here, and then basically every couple memory chips you'll have another bulk capacitor. And this is more common. Well, that's a typical thing you'd see on NVIDIA GPUs. AMD doesn't tend to do that very much, so I assume they're to not do that, we're just going to spread the memory VRM itself out. This also has benefits for heat generation for the VRM, because basically, this entire area, well, there is this VRM down here, but basically it does spread the thermal load of the memory VRM further out. And yeah, so that can benefit the memory VRM temperatures. Now, this just uses more FDMF 3170s, which is absolutely ridiculous overkill for just, 8 GDDR6 memory chips. The end result is that the memory VRM here would produce, if it was pushing 40 amps, which is insanely high. Like, there's no way it's pushing anywhere near 40 amps, but if it was, it would still only produce about 3 watts of heat. Which is, yeah, like, you don't have to worry about the cooling on that whatsoever. Like, honestly, these two voltage regulators are probably getting warmer. Like, the temperature of these voltage regulators is more affected by the heat coming off of, like, this memory chip right here, that one over there, this this phase over here. And for this one, it would be like, okay, like this one has this phase right here, which that would be the VDD. I assume that's the VDDCI. So that actually shouldn't be producing much heat either. So this would basically be primarily heated up by this memory chip over here. So yeah, like memory VRM is insane overkill. And it is a two-phase, and it's controlled by this chip over here, which is another IR35217. And this is another one of those reasons, like this is one of the things you just don't see on all of the custom cards. Everybody else uses an NCP 81022. Why does everybody else use an 81022? Because the 81022 is much, much cheaper than a 35217. As this is a controller that goes all the way up to 8 phases, and AMD's running it as a 2+1 here. The +1 being this right here, which I assume is the VDDCI rail. So that's the rail that's actually powering your memory controller. And of course, AMD went with another 70 amp smart power stage because overkill just doesn't cut it when it comes to powering the memory system. Yeah, so this again is just like none of the custom cards do this because this is just expensive to do and overkill. So it's cool that the reference card basically just goes, yeah, we're just gonna smash like one of the best power stages you can currently get on everything. And I think for AMD this was mostly like a factor of, well, we're buying a bunch of these anyway, so we may as well, like, I assume maybe, well, no, I think it's basically that AMD just didn't want to deal with ordering a bunch of different parts, so it was just a case of, like, we'll just use one power stage for everything, and that can simplify design. But most, add-in board partners, they're actually going to have piles and piles of weaker power stages available to build their PCBs with, to build their cards with. So it's just like, yeah, using a really expensive 70 amp smart power stage where it isn't completely necessary is kind of not, is not going to be something they want to do. So yeah, anyway, VDDCI, insane overkill. And again, this could put out 20 amps with about 1.5 watts of heat. Funny how that works, right? Like 3 watts, 40 amps, 20 amps, 1.5. Yeah. So because I actually don't know how much power the memory system pulls, I would assume that the split is actually something like 10 amps on the memory chips. And then another sort of 10, 15 amps from the actual VDDCI rail. At least if we go by what I saw on GDDR5 cards. Basically, with GDDR5 cards, it was that AMD's memory controller is actually horrendously inefficient. So yeah, it sucks up most of the power in them. So, well, no, like basically half the power in the memory system was actually just the memory controller and wasn't the memory chips. So yeah, I'm assuming the same is going on with the GDDR6. With the GDDR6 memory chips should actually be more efficient than GDDR5. So these should be, well, I'd expect them to pull a bit less than what the GDDR5 chips were pulling. But then again, we also see like a lot of multi-phase designs for GDDR6 power delivery, but that might also just be it wouldn't necessarily be a power requirement. It might just be a regulation requirement, because there's a lot of cards where you actually have a two-phase memory VRM that's not really that powerful. Like this one's really, really overkill compared to some of the designs you see for other 8 gig GDDR6 cards. So yeah, the issue is I've not actually had a chance to measure power consumption for individual bits and pieces of GPUs like this. So Anyway, that's the VDDCI up there. Down here we have what I assume is the SoC, and that's of course controlled by the same controller that handles the vCore VRM, and yes, and of course that is another FDMF3170. So yeah, that's also like the SoC rail is a minor rail. I'd be very surprised if it pulls more power than the VDDCI. So yeah, that's the thing is like basically on the non-reference cards, you'll see like VDDCI, VMEM, VDDCI, VMEM, and SoC get replaced with a bunch of NCP 302155s, which are 55 amp power stages from On Semiconductor. And they're just power stages. They're not smart. So they don't monitor temperature. They don't monitor current. The only temperature functionality they have is basically an over temperature warning that they can send to the controller, and that's it. Like they're as dumb as it gets basically for power stages. So, well, no, you could go one step dumber. You could have power stages without the temperature warning, without a temperature warning system. But you know, like these days, you don't really see that anymore. Well, unless you're going super cheap. And just because the temperature warning system is built in doesn't mean it's necessarily being used. So yeah, that's another thing to consider. But anyway, so yeah, like the reference PCB in terms of like the power stage selection and the controller selection is, well, really, really nice, right? Like you've got a great vCore, you have massive overkill for the minor rails. And then even in terms of controllers, you have massive overkill. Now, one downside to the IR35217 being used basically everywhere is that the NCP 81022 is much, much, much easier to volt mod than a IR35217. Now, the IR35217 does have some advantages in that if you actually get software control for it, this thing is far more capable than an NCP 81022, but getting software control for this thing is kind of difficult. So, yeah, that's... it's kind of the only downside, but yeah, in terms of actual like quality, the reference card is really, really great. Now, another thing that I think is a reason why we don't see the reference PCB used very much is AMD's capacitor selection. These right here on the input filtering are tantalum polymer capacitors. These are basically just like, they're very expensive. That's all you really need to know about them. They are far more expensive than your through-hole aluminum polymers. Now, they do have some electrical performance advantages over through-hole capacitors, but basically, if you're a add-in board partner, well, you don't want to pay for these. Like, you really don't. The main reason I think AMD is using them here is because they need to clear the blower. And that's just kind of it. Like, there's no, like, if they weren't using a blower heatsink, I'd be very surprised if they hadn't gone with a cheaper capacitor. But as it is, they just need to get the capacitors to be low profile. And that's one of the things that, like, the tantalum polymer capacitors solve is, like, they're low profile, they're very compact, you get a high capacitance in a very nice compact package, and you pay through the nose for it. Which is why basically, you know, nobody wants to use the reference PCB for anything because it's just like, yeah, nope, don't want to pay for that. Similarly, if we look at the back of the card, and even AMD agreed that they don't want to pay for the massive array of aluminum polymers that they designed the back of the card for. And these, again, like on basically all of the custom cards will replace the bulk aluminum polymers with a bunch of, the SMD aluminum polymer capacitors that we see here. They'll replace all of these with through-hole aluminum polymers. And you might be like, well, that's the same type of capacitor. What's the difference? Well, the SMD ones have they can have an ESR advantage, but they basically always have an ESL advantage. And what that basically means is these are better. Electrically, these have better performance, but there's one downside to these. You can't get them in a high endurance. Well, there's kind of two downsides. One, they're expensive, which is again why nobody really wants to use them. And two, you can't actually get these in very high endurance ratings. Basically, you're stuck with 2,000 hours at 105 degrees Celsius, which kind of sucks for the reference card because this one, like the reference card's cooling is inferior to all of the custom cards. So these I think would be better suited towards cards with proper cooling systems. But AMD's obviously using them here because, well, there's a blower on the front. You can't have, tall through-hole capacitors getting in the way of the heatsink. So that's why we end up with a bunch of these on the back of the card. But yeah, I'm a big fan of these, but even AMD agreed that, you know, as great as these are, they are very expensive. So they left a very large amount of them just unpopulated because it's like, well, those, the thing is just like, there might be a measurable difference if you actually populated all of the unoccupied pads. In terms of overclocking, you might see like a 10 megahertz improvement, maybe a 20 megahertz improvement. But basically the idea is just like this doesn't make a notable basically this is enough to run the card at stock. And that's all the manufacturers like internet manufacturers and AMD care about when it comes to, you know, configuring the capacitors. The engineering sample boards probably had all of these populated, and then at some point they were like, well, are these all necessary? And then it's just like, well, for the clocks we want to run, no. And that was how all of these went missing. So yeah, and similarly we can see that, you know, they had option, like these might be just optional, or it was just like during design it was like, we aren't like, do we need maybe more capacitance? So just in case you'd have the extra pads on the back. We also do have some multi-layer ceramics, of course, in the VRM, and those are just kind of jammed in between the inductors. So you actually, like, one of the big interesting differences to me with the reference design compared to a lot of the custom cards is on the custom cards, you'll actually, because they're using those big aluminum polymers that go through hole, and those have an ESL disadvantage, you'll actually notice that those cards will have a bunch more multi-layer ceramics on the directly on the output of the V-Core VRM, because they're basically trying to compensate for the fact that the through-hole aluminum polymers are, for lack of a better term, slower capacitors than the SMD ones that AMD is using. So multi-layer ceramics are very, very fast. And through-hole capacitors aren't, like, they can get pretty fast, but they can't be anywhere near as fast as multi-layer ceramics. But the SMD type capacitors can actually sort of hit a sort of middle ground where they'll approach almost multi-layer ceramic like performance. So yeah, that's kind of why, you know, AMD basically has a bunch of the SMD ones and then just a few multi-layer ceramics just sort of squeezed in between the inductors. And then if you look at the reference card, you'll actually see a lot of multi-layer ceramics to complement the through-hole aluminum polymers. So yeah, that's kind of a, you know, like, and again, it's just like for the design that you actually see on most of the custom cards is actually cheaper. It might actually perform the same or better, especially since a lot of custom cards will, like, there's some custom cards which will actually go to high, like more, like you'll end up with more overall capacitors than like any other, well, just there's differences in the capacitor configurations. We're not going to get into that here, because otherwise we'd be here forever. But basically, like, there's a lot of design decisions with it, like the reference PCB here, where it's just like expensive and unnecessary, expensive and unnecessary, expensive and unnecessary if you're not using a blower heatsink, right? If you go on the back, expensive and unnecessary. Like there's a lot of things that oh yeah, more expensive and unnecessary. For the memory VRMs, again, like you have tantalums over there, so, and SMD polymers. Most of the non-reference cards don't bother with those. They just throw a through hole and a bunch of multi-layer ceramics to help it along. So yeah, it's kind of like, if I wanted to like mess around with the card, I'd probably pick the reference card for modding, just because it's like, well, that's an easy thing to fit. Like, those are easy to fill out. I wouldn't bother with any of these. Those don't usually matter that much. Yeah, but then the biggest issue is, of course, the controllers. So, yeah, but again, like, if you're just going to be water cooling, I really like the reference card. The one thing I don't like about the reference card is the fact that AMD, like, they have a history of including BIOS switches on their cards, and then with the 5700 and the 5700 XT reference card, they didn't bother. Admittedly, there's not really much you can do to the BIOS with a 5700. Like, the most you can do is just, like, take the BIOS of a different card and flash that onto your card, but it's just like, like, you know, that's a relatively safe thing to do. It's not like custom BIOSes where it's just like, well, I don't even know if this is, like, well, especially if you do all of your mods yourself, then it's like sometimes you'll make some adjustments and be like not 100% certain that they'll actually work, and then you flash it and then it's like, oh, it doesn't boot. That's I gotta go fix that. And the BIOS switch can be extremely convenient in that scenario. But yeah, with 5700 XTs, like if you change anything, like if you try to manually mod the BIOS at all, like you already know it won't boot, so there's no point trying it, right? So yeah, it's kind of it. Oh, and I think, well, there's a bunch of minor voltage regulators that we actually see on the card as well, and they're not on the back, so it's fun. Basically, there's going to be a 1.8 volt supporting rail for basically the BIOS chip and the GDDR6 memory chips. And that's going to be maybe this, maybe that, maybe this. I'm not entirely sure. The issue is, like, I don't have the card in hand. And a lot of these small voltage regulators, it's just like, I'm not sure which one does what. There's also going to be a PEX rail for the PCIe interface and potentially a display drive rail, or there might be two 1.8 volt rails. This card actually has a really, like, compared to a lot of the custom cards, there's a bit too many tiny little voltage regulators in this area, as well as that one over there, right? Like that one I think is 5 volts just because it's so far away from anywhere useful, but there could easily be like two 1.8 volt regulators for some reason. Well, yeah, that actually, there's your BIOS chip. So if that was 1.8 volts, and then here we have all, well, yeah, I'm not sure. I'm really not sure why this has so many, like why there's 3 minor regulators on this card, because the custom cards don't bother with that. They just have 2. So yeah, I guess maybe what the AMD has 2 1.8 volt rails or something, which is not that uncommon. Like I think reference NVIDIA cards sometimes do that as well, where you'll have a 1.8 volt specifically for the BIOS and another 1.8 volt specifically for the GDDR6. But yeah, that's pretty much it. That's the reference card for the 5700 XT. And yeah, as I said at the start of the video, if you just want to water cool your 5700 XT, I don't really see a reason to like go for a different PCB, because this one's already really, really good. Most of the custom, like most of the non-reference cards are basically like they're essentially cost, like most of them are cost optimized. Some of them are like cost optimized and then upgraded. So they first, down cost the design and then add a bunch of phases back on. Well, not back on, but add a bunch of phases above the reference design and, tweak some things like that, add like features like BIOS switches or fuses and that kind of thing. But ultimately, fuses don't actually help the end user. They're mostly for RMA purposes for the actual vendor, not you. Because ultimately that fuse is going to blow, and the only thing it's going to help is their troubleshooting process, not you. Because it's basically that's all the fuse really, like the fuse is very unlikely to be either fast enough to protect anything, or well, more like it, well, yeah, pretty much it's not going to be fast enough to actually prevent a failure. It's just going to, like, once the failure has occurred, it's going to prevent that from spreading, essentially, which doesn't really help you because you're not going to be able to repair the failure in the first place. So, yeah. Anyway, yeah, that's it for the video. So, thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what we do here at Gamers Nexus, then we have a Patreon where you can support us directly. There's also store.gamersnexus.net if you'd like to pick up merch, like say the mod mat that you can see in the background of the video. Yeah, that's it. Oh, and I also have a channel called Actually Hardcore Overclocking, where I do more videos like this, as well as videos about other overclocking related things. So that's it for the video. Thanks for watching, and goodbye.